Okay, here will be the first video for topic 2, and it's going to be about cyclic groups. I'm going to, again, just like with the first one, sort of follow along with these mini lecture notes. Some of this I've already done, so just to be clear, so suppose we have a group G, and we have G in G, okay? This will be a group. I'll use the multiplicative notation. Well, I'll use both, but mostly the multiplicative notation. Then we define this guy, G, to be the set of all Gi, I, and Z. And we verified last time that this is a subgroup, right? So this is a subgroup of G. This is the cyclic subgroup of G generated by G, by little g, right? And if group G is equal to this thing, then we say G is a cyclic group. So something's a cyclic group if it has a generator that generates it all by itself. Okay. If we really, if this is infinite, right? So I mean, maybe this repeats, over and over, right? If it does, then it's finite, and we proved that last time, right? So we showed that if G is finite, then G equals E, right, and then G up through some G. In fact, if G is finite, in fact, let me say this. Let's see, G has size n, right, which is less than infinity. Then this thing is going to be this guy up to Gn minus 1. So it'll be cyclic. This is cyclic, but it'll look like that, right? And so this will be, isomorphic to Zn. Which we also call Cn. I think maybe your book also uses that for the cyclic group. And if we're doing additive notation, just to throw that in there, right? So if the G was like plus and 0, right? Then this generated group wouldn't be multiples of G, right? So these are G times G times G. It would be sums, right? So it'd be the set 0, because that's what we use with additive notation. We have G. You would have 2G, right? And we go on up to n minus 1G, right? Like that. So this would be, G plus G plus G plus G n minus 1 times. Whereas this was G times G times G, n minus 1 times, right? Let's see. Now we want to get a little bit of information about these things. Let's see. So I'm just going to go through these items here. So let's see. So the first one is that GK is equal to E if and only if. Let's see, in this case, here I'm in a finite cyclic group, right? And I'm assuming G has order n, right? So GK is equal to E if and only if the order of G divides K, right? That's what I claim. Now, what have we already proved? We've proved that, that what G is here, right, is the set E G to the, let's see, we're saying the order is n, right, to the n minus 1. Right? We're assuming here that the order of G is n, right? That's part of the assumption here. Okay, and so this right here would be n, right? N divides k, right? And so what we have here is this. We would have G to the k is equal to G to the Qn plus R. We have a remainder theorem, right? And so this is equal to G to the N to the Q, G to the R, right? This is E, so this is E to the Q, GR, so this is just GR, right? Like that. And in particular, GR is not E, right? Unless R equals 0, right? So this does not equal E unless R equals 0, right? But if R equals 0, then that says that K, so if R equals 0, then K is equal to Qn, right? So and hence, so k is equal to qn, so n divides k, which is what we wanted to prove, right? That is, because n is the order of g, so the order of g divides k. Okay, good, right? So that's how you prove the first one. I'm just going to work through the proofs of these things that are stated here. Let's see, the next one says gi inverse is equal to g minus I. Okay, and this is equal, again, we're in the situation, so throughout this we have that the order g is n, this is equal to g n minus I. Let's see, so how do we get this? So let's show that gi inverse is that thing there, right? So gi times gn minus I, right, is equal to, well, this is going to be gn, right? And similarly, gn minus I, gi is gn, right? But these are both e, right? And so in particular, this thing behaves like an inverse to gi, and we saw before that anything that behaves like an inverse to gi is an inverse to gi, right? So gi inverse is equal to gn minus I, which is what was claimed. Let's see, the other one I claim here is that g minus I, and so what do I actually mean by g minus I? Yeah, so I guess by g minus I literally just mean g minus 1, g minus 1, I many times, right? And so the claim is that this is also equal to gi inverse, right? So I can multiply that by gi, but how do I write gi? Sorry, these are all ones, not i's. And that I would write gi as g1, if you like. G1 I many times. There's I of these. There's I of those, right? And it's clear that these, oops, let me just scroll that up. Let's see. I don't want to scroll that up yet. It's clear that we can pair these off, right? And they'll cancel out, so this will be E, right? And then we can swap the order and do that in the other direction, right? And let's see, so just to be clear here, whoops, sorry about that. Let's do this. Just to be clear here, what I have written here is g minus I gi, right? It's equal to that, and that's equal to E. And we could flip it around and say gi minus I is equal to E, right? And so we're getting that this is the inverse to gi, right? And again, that means that it is gi inverse, right? So these things tell me that g minus I is gi inverse, right? And so now we get the equality of all these things, right? That is equal to that is equal to that, right? So they're all the same. And that's what that says there. Let's see, the next one says gi equals gj, IFF, n divides I minus j. Okay, this isn't surprising because this is like the, I've already said that, the cyclic group, if it has order n, is like Zn, right? So we should be getting something like the modular arithmetics. We're getting that powers of g are the same, assuming that g is finite, the g has finite order. And so these powers are the same if n divides the difference, right? Which is exactly the same as the modular arithmetic. So in other words, I could rewrite this as g I mod n equals gj mod n, right? That would be saying the same thing. Because that's just how, that's one of our equivalents to, this relation. Whoops, mod n, right? There's two ways of writing that. One is to say n divides I minus j, another one is to say that I mod j equals j, or say I mod n equals j mod n. So how do we prove that? Well, we're just going to use the thing above, so I can just, let's say, suppose I is less than j, just to to be specific, right? If it's not, we can flip it around the other way. Or let's say I less than or equal to j. I can do like that. Then I can multiply both sides by g minus I, right? And so I get E is equal to gj minus I. Oops, j minus I, right? And since E is equal to gj minus I, from the thing we did above, that's going to tell me that n divides I minus j, j minus I, right? Okay, and if it divides j minus I, it divides I minus j. You don't have to worry about the order there. That's like the symmetry of this relation, right? Good, so that does that one. Let's get this next one. So I'm going to claim that gi is equal to gcd of I and n. Now again, let's just be careful here. So again, we're assuming here that this has order n, right, when we're doing this. And here the point is this. Let me see, how do I want to say this? I think this is what I want to say. So I generate by I here, right? So I have, I mean, what do we have when we generate? So we get, g I gi squared, right? Because we're basically generating with this, right, etc., up through g I k, right? So we'll have a set like that, and eventually we're going to hit E, right? We've seen this before, right? So that what we're actually getting here is like this. We're getting, we get E down here, right? And then I'm going to have gi, then I have g2I, like that, up through g k minus 1I, right? So we'll have that, okay? And, the point is that each one of these things might be, so the original G, right? Here's where we have to be a little bit careful. So the original G is like this. It's, E, G, etc., right, up to G n minus 1, okay? So these things might be, bigger than n. I mean, I don't know what I is, right? So the point is, each of those things up here are equal to something less than n. And in fact, what we can do is we can just mod out by n, right? And so this set here is really the same as E, gi, g2I mod n, etc., right? So up to gk minus 1, I, mod n, right? So I can mod in these things. Why is that? That's because g to the n is E, right? So just like I did before, right? I can, I mean, just to be clear about this, right? So let's say g to the si, right, is equal to g to the, so si is equal to qn plus r, right? And where this is the where r is equal to si mod n, right? And so this would be gqn plus r, right? And just like we did above, this will be gr, right? So this is g si mod n. Okay. Okay, so once we get that, then we can take, so the least index after we mod out, right? And whatever the least index is, that will generate this whole thing too, right? So in some sense, we're looking at powers of gi, but we're really interested in those modulo n, so that we can sort of reduce them to least terms in the sense of powers of g, and then it's kind of taking the minimal thing, and that's going to generate the same set, right? So that's sort of what we're interested in. And then the claim is that minimal thing will actually be the GCD. So that's kind of what's going on, right? So here I'll actually do this in a slightly different way. And actually this proof is here. So I'm going to have let D equal the GCD of I and N. Okay. Then we know that there is some x and y, such that xi plus yn equals d, okay? And we're going to see now that g to the d equals g xi plus yn, right? Now, so this is g, let's see, g I x g in y. And so just arranging these in a specific way, right? So this is the power of gi. This is e to the y, right? So this is just gi x, right? Like that. And so what I'm getting here is I'm getting that gd is contained in gi, right? Because gd, this is the greatest common divisor, is a power of gi, right? And that's using this Bezo's theorem again. The other direction is kind of trivial. Gi is certainly contained in gd, right? Because the minimal thing, right, that's going to, because the thing's going to divide, well, it divides I, right? So, gi is, because I is equal to kd for some k, right? Okay, so gd to the k, right? So gi equals gd to the k, right? Which is an element of that, right? So what we get here is we get the gi equals, the subgroup generated by gi is equal to the subgroup generated by gd. Okay. When you think about it, because of the divisibility thing, this is going to be the least index of G. So that's what I was saying before. You're sort of taking the least index of something that generates this whole set, right? That was kind of what I was looking at before. Okay. Good. All right. So that does that. So we have so just to reiterate, just to rewrite it like this, we have that. Just let me just say the whole thing again. So we've got G as order n. Then if I generate it by gi, and this is the same as generating by gcd of I and n. Okay. Now notice when you're going to get the whole group G back, right? So in particular, gi equals G, right? You get the whole Cyclic group back if and only if gcd of I and n is 1, right? So they're relatively prime. So when they're relatively prime, right? So in particular, the number of generators, because anything that generates the whole group, generators of G, right, is equal to phi n, right? Because you're looking at powers of G, because those are the things in the cyclic group that generate the entire group, right? So there's phi n many of those things. So there's all sorts of useful stuff here, right? So, I mean, we're going to use this. So that gives you a way of telling whether or not you have a generator. You have a generator. So G, so you're in a cyclic group generated by G. A power of G, G to the I, generates the whole group if and only if the GCD of I and N, right, is 1, right, if they're relatively prime. So that's the point. Okay. Let's see, the next thing is kind of equal to, so we have the G, so we have that, again, if D equals the GCD of N and I, right, then we have that GD, right, equals GI, right, they have the same order, okay, and clearly, this is the minimal index in there, right, and so this is going to be, so the group generated GD, right, is going to be E, then we're going to have GD, right, all the way up to G K minus 1 D, right, like that. And what we're going to have here is a K minus 1 D sorry, like one more power up, right? So GKD is equal to E again, right? So if we go one more power of GD up, right, because that's what's generating here, we get back to E. Good, all right. Yeah, and so what does that mean? It means that the order, right, the order of GD, which is the order of GI, right? So this is equal to N, right? Is K, and that is exactly N over D, right? So that's important. So that's kind of a proof. What we get as a result, right, is that the order of GI is equal to N over the GCD of NI. That is what we have here. Okay. Good. Okay. Let's see. I say some of the same things in additive notation, so there's nothing new there. Okay, I want to finish up with just a couple of useful results. Gaussism is going to turn out to be interesting for a few things. So here we're in a situation where we have an element of a group G. It has order N. Let's see. Oh, well, let me just say what we're going to prove. So we're going to prove this. We're going to prove that for any N, N is equal to the summation of the things that divide N, phi of D, like that. And let me just point out now that, if we're looking at D's that divide N, that means N over D is also something that divides N, right? So if I take N and divide by D, then that gives me something that divides N. So this is actually the same as summation D that divides N, phi of well, I can just say D over N. Sorry, N over D again. I mean, what we're doing is we're summing over all the divisors of phi of D, and here I'm writing the divisor like this. Here, sort of this is the divisor, right? So I'm saying, in some sense, N over D divides N, but then D also divides N, right? So anyway, think about this. These are actually the same set of numbers, right? I don't know. It kind of seems strange, but right. But these are actually the same set of numbers. So we'll use that in this proof. And so we're going to start off with this. We're going to do this with a nice little sort of set theoretic construction. So SD would be the set of all GI. So it's to the order GI. And we're working in a group where G is order N, right? Is equal to D. So one thing we notice is that D not equal to D prime implies SD intersect SD prime is empty. And we also have that G. Everything has some order, so this is a union of SDs. Oops, right? So in particular, we get that N equals the size of the union of the SDs, D divided N. And this is equal to, because these are disjoints, it'll be summation D divides N SD, right? And then what we're going to show is I'll just say we're going to show that, so we'll show, I mean, in some sense we've already done it above, but I'll sort of show you how, that SD equals, nope, so go away, come on, go away, equals phi N over D. All right, we're going to show that the size of SD is equal to phi of N over D. So then we'll get that N equals summation D divides N phi of N over D. Yeah, maybe I wrote sort of a little funny what I wanted up there, but no, I guess this is really what I wanted. So this is going to be the same as phi of D divides N phi of D. That was from the little comment above, right? And that's what we're trying to prove, right? So the main thing is showing this, and actually in some sense I've already done that. So, but let's just sort of go through it a little bit carefully. What I have here is I have that GI, the order GI is equal to N over the GCD of N and I. Okay, now we've saw that above, right? And now in this case, we also know that GI, and this is for GINSD, right? That's what I'm interested in here. And so I know that this is equal to D, right? But then I can, sort of manipulate this and get the GCD of I and N is equal to N over D, right? So I get that. Now in that case, now the other thing I have is I have the GI is actually equal to G of the GCD of N and I. We've seen that above too, right? But now this is, because of this is just equal to G to the N over D, right? So it's got like that. So in particular, for every GI and SD, I get the GI is N G N over D. Okay, so now I'm sort of in this situation where I'm looking at things, with a certain, I want to say it with a certain, yeah, sorry, no. So each one of these are generators, right? So I'm looking at, so everything in here is a generator of this, right? So I'm just looking at the generators of that, right? But now we're in a situation where I'm just looking at generators essentially of, whatever this is, whatever this would be like, this is an integer, right? D divides N, so whatever Z of N over D is. So the point is that the number of generators of that thing is phi of N D, right? The set of things relatively prime to N over D, right? So we get that. Sorry, there are this many generators, right? So what I'm getting here is that SD, this is what I wanted to get, is equal to that, right? So it's important that we get all of these things into one single cyclic subgroup, right? If they're in different cyclic subgroups, we get something slightly different, right? In fact, that's what the next little result is going to be about. But this does it, right? So this actually does it because of the counting argument I had up there, because this was the thing we needed to prove. So we're done. Okay, so that's Gauss's lemma. Think about that. That's a good useful lemma. We're gonna use this, for example, to show that in a finite field later on, the multiplicative part of a finite field is always cyclic, which is not at all clear. But we use essentially this argument. We use this as part of the argument anyway. The next one kind of looks at this again in the case where the set of things of order D is not sitting inside a single group. That's kind of the point with this next result. So here I'm in a group G, and I've got some things. Let me even see what I've got going on here. Let's see, I've got some elements of order D. Right, and I want G. Yeah, and so I've got two elements of order D, and I've got GA is the set of all generators of A, and GB is the set of generators of B. Okay, and so in particular, we know that phi of A equals, let's see what I want to say. I want to say, sorry, phi of D. Phi of D is equal to the size of GA, right? So the size of GB, we know that, right? And I want to say that, so one of two things happens. Either GA is equal to GB, right? So they're just generating the same cyclic group, or GA intersect GB is empty, right? I mean, one of those two things has to happen, right? Because if there was anything in common, then that thing that's in common would generate the whole group. So they'd have to be this, they'd have to actually be the same. So either these are the same, or they're different, or they're completely different, right? And so what that means is we know then that and so the things that are in these generator sets are exactly the things that have order D, right? So when we look at the set of all A, such that order A equals exactly D, right? So when we're looking at those things that have exactly that, this is exactly equal to the the union of all these GAs, right? Where A has order D, right? And those are either the same or disjoint, right? So in particular, this is some multiple of the size of GA, right? So this is some K times the size of any one of these GAs, which is phi D. So this is like K times phi D, right? So what we're getting here is we're getting that phi of D divides the set of all A such that A equals D. So this is the order of A equals D. Right. Now, what we got above, in the case that we're sitting inside of a cyclic group, right, is that that this set had size exactly phi D, right? So in other words, this K would equal 1 in that case above. That's sort of what we were doing above, just to make this a little bit more clear. So in the case that we're not in a cyclic group, we're just in any group, right? Then we end up with this statement instead. Okay, and that's all I wanted to do for this. And that does the cyclic group part of these notes. And so the next thing will be the symmetric group, which is another interesting topic.